So, hi guys, am I audible? Just confirm once. So, how are you all and how was the contest? You may write in the chat. Okay, I hope the screen is also visible to you all. So, I guess we can start. So, hi guys, this is Abhinav and welcome to the post-contest discussion of the CodeChef Starters 206. Okay, so let's discuss. So today we'll discuss all the problems from div 1 as well as div 2 of the CodeChef round. So the first problem from div 2 and all the 5 problems from div 1. So 6 problems we'll discuss. Okay, so I guess we can start now. So yeah, so the first problem is prime sum. Ceph has an integer array D of length n such that AI is from 1 up till 3. Ceph is wondering how many pairs exist in this array which have a prime sum. Formally find the number of pairs ij such that I is less than j and ai plus aj is prime. Basically, you have to just find how many pair of indices I and j exist such that the sum of the values at those indices is prime. And you know what a prime number is. One is not prime, rest of the numbers are prime if they have exactly 1 and x as their divisors. So the values of the array are only 1, 2 or 3. Only 3 possibilities for the value of the array, and the length of the array is up till 100 only. Okay, so this is like pretty simple if you think. So you have an array A given to you which is of length n, and the values in the array are either 1, 2 or 3, only among these. Now you just need to find out whether if you take any pair of indices from this array so that ai plus aj is a prime number. So you have to just count how many such pairs of indices ij exist such that this is prime and I is less than not equal to I is less than j. Okay, so you have to find the number of ordered pairs. Okay, not unordered pairs. So when would the sum of ai and aj would be a prime? So for the values of the array we have only three options, 1, 2 or 3. So if we get 1 plus 1 we get 2, this would be a prime number. Or we may have 1 plus 2 where we would get 3, this would also be a prime number. Or we may have 1 plus 3 which we would get 4, 4 is not a prime number. Or other possibilities is 2 plus 2 where we would get 4, again it is not prime. Or we can have 2 plus 3 where we would get 5 which is prime. Or we could have 3 plus 3 where we would get 6 which is not prime. So picking, if you are picking any two numbers among 1, 2 and 3, these are the only 6 possibilities for the unordered pair. Obviously for 1 plus 2 you can have also have 2 plus 1. Okay, but if you take in sorted order, then these are the only 6 possibilities, and we would also have to consider the other way around. But okay, so among these 6 possibilities, the only valid possibilities where we get a prime number is 1 plus 1, 1 plus 2, 2 plus 2 and 2 plus 3. Sorry, not 2 plus 2, only 3, 1 plus 1, 1 plus 2 and 2 plus 3. These are the only 3 possibilities where we can get a prime. So basically we have to just pick any two values such that either both the values are 1, or one of the values is 1, one of the values is 2, or one of the values is 2, one of the values is 3. So how do we count the number of ways to do that? What we can do is, from the array A we may have, let's say 1, 1, 2, 3, 1, 2, something like that array is given to you. So how many ways we can have 1 plus 1 is, we have 1, 2, 3 times we have 1. Among these 3 just choose any two of them. So 3C2 would be the number of ways to have 1 plus 1. Okay. How many ways can we have 1 plus 2? Okay. So whatever is the frequency of 1, pick any one of them. Whatever is the frequency of 2, pick any one of them. So there are 3 ways to pick a 1 and 2 ways to pick a 2. So 3 into 2 would be the number of ways for that. And what are the number of ways to get 2 plus 3? So pick any one of the 2's and one of the 3's. So there are 2 2's and 1 3. So these would be the number of ways for 2 plus 3. So what we can say finally, what is our answer? Our answer is basically for 1 plus 1, we can say whatever is the frequency of 1, if f of 1 represents the frequency of 1, then frequency of 1 C2, which is frequency of 1 into frequency of 1 minus 1 by 2. Okay. So pick any two of the ones. This is the number of ways to do that. Plus number of ways to get 1 plus 2 would be whatever is the frequency of 1, that many ways to pick a 1, and whatever is the frequency of 2, that many ways to pick a 2. So these would be the number of ways to get 1 plus 2. These would be number of ways to get 1 plus 1. And for 2 plus 3, number of ways would be frequency of 2 multiplied by frequency of 3. These would be the number of ways. So if you compute from the array, if you compute the frequencies of 1, 2 and 3, then which just iterating through the array, you can just maintain and compute the frequency in order of n, then your final answer can be written using this formula. Okay. So I hope this thing is clear to you. The implementation would be quite simple. So what I did here is I take this frequency vector of size 4 so that I have indices 0, 1, 2 and 3. So then I take the input and do f of ai plus plus. This way I'll in f of 1 I'll get the frequency of 1, in f of 2 I'll get the frequency of 2, in f of 3 I'll get the frequency of 3. Once this frequencies is computed, my final answer is, as the formula I had written, f of 1 into f of 1 minus 1 by 2, f of 1 into f of 1 minus 1 by 2, f of 1 into f of 2, and f of 2 into f of 3. Okay, this is my final answer. I print that answer. Okay, so I hope this first problem is clear to you all. If you analyze the time complexity, then this loop is taking an order of n time, and this is order of 1 constant operation. So overall, for computing the frequencies, we take order of n time, and space complexity is again order of n for the input array, nothing else. Okay. So I hope this first problem is clear to you all. Can we move to the next? Okay, so let's move to the next problem, which is gladiator fighting. So there are n gladiators standing in a field. They will fight till only one gladiator is left, and the other n minus 1 gladiators have been defeated. Okay, so initially everyone has a skill factor of 0, but every fight that a gladiator wins, his skill factor increases by 1. So initially all of them start with a skill factor of 0, and whenever two of them fights, after the fight, for the winner, his skill factor would increase by 1. And after exactly n minus 1 round, each round two gladiators who are yet to be defeated. Once a gladiator gets defeated, he is out of the game. So when two gladiators who are yet to be defeated will come and fight, and one of them will win and the other will be defeated. The entertainment level of a fight between the gladiators is skill level x, between gladiators of skill level x and y is x plus 1. So the sum of their skill levels is the entertainment level of a fight. Note that it is possible for the lower skill gladiator to win. So it is also possible that the lower skill gladiator can win. It's not compulsory that always the higher skill gladiator would win. So now you need to find what is the minimum and maximum possible sum of entertainment level of all the fights. So you have n minus 1 rounds of fight. Whatever entertainment level you get from each fight, then you can make either any one of them win, and depending on your decision, you would have different sum of entertainment levels. You have to find the minimum and the maximum possible. Okay, so n is given up till 100 only. So if you look at some of the test cases, n is 2, 3, 4, 5. These are some of the test cases. So as input, you are just given an n. let's say you have n is equal to 3. Okay, so for n equal to 3, you would have to find what is the minimum sum of entertainment levels you get and what is the maximum sum of entertainment levels you get. So how do you get the sum of entertainment levels? So n equal to 3, it means you have 3 players, 1, 2 and 3. Okay, initially all of them have a skill of 0. This is their skill level, all of them have 0. Now since n is 3, so there would be n minus 1 rounds of fight, that is 2 rounds of fight. Okay, in every fight one of them gets defeated. So after one fight, remaining players would be n minus 1. After 2 fights, remaining would be n minus 2. Same way, after n minus 1 fights, only 1% would remain. Okay, so always n minus 1 fights would be required for 1% to remain. Okay, so here what may happen, let's say these 2% fight together. Okay, then after the fight, since both of them has a skill level of 0, whoever wins, let's say 1 wins, then 1 would now have a skill level of 1 and 2 would now would get defeated, and it would just, it had a skill level of 0, it would remain 0 and it would get defeated. And then this 3, it had a skill level of 0, it would remain. So if 1 wins here, we would have 1 with skill level of 1 and 3 with skill level of 0. Then these both would fight together. When these both fights together, so in the initial, for the first fight, here both of them has a skill of 0. So 0 plus 0 equal to 0 is the entertainment level that we get here. Now for this particular fight, this has a skill level of 1, this has a skill level of 0. So the entertainment level we get for this fight would be 1. And after the fight, if let's say 1 wins, then 3 would be defeated. If 3 wins, then 1 would be defeated. Whoever wins, doesn't matter. After the game ends basically. The sum of entertainment levels that you get is 0 plus 1. So 0 plus 1 is equal to 1. Now, whatever other way you do, let's say in the first, you maybe you assign 2 and 3 to fight together. So in the first fight, always one of them wins and he would have a skill level of 1, other one gets defeated. So the next fight would be between a skill level 1 and skill level 0 only. So in this scenario, for n equal to 3, always the first fight would have an entertainment level of 0, second would have an entertainment level of 1. So it would be 1 only, both the maximum and minimum. So 1 comma 1 would be your answer for this test case. For n equal to 3, 1 and 1 would be answer for both. 1 is both minimum as well as the maximum. Okay, let's see for n equal to 4 what happens. So for n equal to 4, what we can say is we have 4 people. Okay, so initially all of them have a skill level of 0. Okay, let's say any 2 of them fights together. So with this fight, 0 plus 0, you get 0 entertainment points. Okay, and let's say one of them gets defeated. So now this one would have a skill level of 1 now. Okay, as 2 gets defeated. Now even if you defeat 1, the thing remains the same. 2 would have a skill level of 1 and 1 would be defeated. Still 3 people would be left. Next fight, either we can make 3 and 4 fight together, or we can make 1 fight with 3. Okay, so let's consider this scenario first, where we make, let's say 1 and 3 fight together. So 1 plus 0 is equal to 1 would be the entertainment level of this, and then any one of them could win. Let's say 1 wins and 3 gets eliminated. So in this scenario, the entertainment level, the skill level of 1 would increase to 2, and the last fight would be between 1 and 4. And with this fight, we would get 2 plus 0 is equal to 2 as the entertainment level. Whoever wins, doesn't matter. The total entertainment we got from here is 0 plus 1 plus 2. So 0 plus 1 plus 2 was 3. Okay. Another way to fight was, instead of here making 1 win, let's say we made 3 win here. Okay, so this had a skill level of 1, and in this fight, let's say instead of 1, 3 wins this time. So if 3 wins, 3 would have an entertainment a skill level of 1, and in the last fight, 3 and 4 would fight. 1 plus 0 is equal to 1 would be the entertainment quotient here, and whoever wins, doesn't matter. Total entertainment we got is 0 plus 1 plus 1 is equal to 2 in this case. Okay. Another way to fight was, let's say in the second fight. Okay, so after the first fight, 2 gets eliminated, one gets 1 skill level. Let's say the next fight is between 3 and 4. So if you make 3 and 4 fight together next, then 0 plus 0, 0 would be the entertainment level here, and whoever wins, it would be the symmetric only. you can understand. So let's say 3 wins and he 3 gets a skill level of 1, and then these two would have to fight with a entertainment level of 1 plus 1 equal to 2. So total entertainment we got here was 0 plus 0 plus 2. So 0 plus 0 plus 2 was 2. Okay. So here you can see we tried different methods, and the final entertainment sum that we got was sometimes 3, sometimes 2, sometimes 2. So the minimum here was 2 and the maximum here was 3. I guess for this test case, this is the answer. 2 is the minimum, 3 is the maximum. So this was the answer for this test case. Okay. So basically you have to optimally find what is the minimum you can get and what is the maximum you can get using these fights for a given n. Okay. And the constraints are n equal to 100. So you can do even up till something n cube type of thing. But okay, we'll do it more optimally only. So let's see what exactly is happening in how can you make. First let's try to find maximum, then let's try to find minimum. Okay, so if you want to maximize the total entertainment quotient, how would you maximize it? If you try to think, so initially all of the n people have 0. Okay, so whenever any two of them fights, for the first round your sum for the value for the entertainment level you would get would be 0 only. Two of the 0 and 0s fight, and after the fight one of them would always get eliminated, and for one of them their entertainment level would become 1. Okay, now from the second fight we can decide what we want to do. So from the second fight, either we have two types of option, either make a 1 fight with a 0 or make 2 of the zeros fight. Okay, now we want to maximize the total entertainment quotient. Okay, so if we make 2 of the zeros fight, then again we would get a 1, value would remain 0. Again, if 2 of the zeros fight, again the value we get from that would be 0 only, and we would build up some 1 Then if 2 of the ones fight, then we get 2 entertainment quotient. But again you can see that with every fight you are adding a +1 to someone. Okay, and that +1, whenever he gets killed or he wins, in both of the cases that +1 gets added. Okay, so whenever there is a fight between two people, okay, so between two people I and j, so si and plus sj is the total entertainment quotient that we get. So if let's say j is getting defeated, then whatever skill level j had, that gets added to the answer, and what we get from si, whatever skill level I had, that get added to the answer, and then again that si got increased. Then again if he fights with somebody else, that an increased si would again get added to our answer, and from sj always the defeated values would get added. So if I'm telling that if you look at any one person, let's look at the ith person, so he would, let's say, win for some rounds and then he would lose. So until the time he is winning, for the first win it would add 0 to the entertainment level, for the next win 1, next win 2, up till if he is getting x number of wins and then he loses, then plus x till x minus 1, that much would get added to the skill level, and when he loses, then again x would be his skill, x would get added. Okay, and if you look at all the people, total number of wins would be n minus 1, total number of losses would be n minus 1. So if you are making one person to win more times, the value you are adding to your answer is getting increased every time, the more wins he is getting. Okay, and if the win loss is divided, like some jth person, he start with a win and that then gets a loss, then for this win you add a 0, for this loss you add a 1. So for any person it would be some streak of wins and then a loss, making sure that when you add up the wins and losses for all the people, the total number of wins is n minus 1, total number of losses is n minus 1. So basically if you are taking out a win from someone and adding it to someone else, then like you can see that For the 0th person, it would be some number of wins and then a loss. For the first person, some number of wins and then a loss. Same till the nth person, or if you start with 0 till the n minus 1th person, some number of wins and then a loss. Now you need to make sure that total number of wins and losses are same. Then if you are adding more number of wins to some person, then some person would have directly a loss. Okay, so what is the value getting added to your answer? For this case, the length of the sequence. So if this length is, let's say, 5, this length is, let's say, 2, this length is 2, this length is 3, something like that. So what change you can do? You can take one win out and push it here, make it 4, make it 3. What would be the most optimal? Since you know, if you just extend one of them very long, then this sum is just getting increased. So if let's say you give all the, if for one of the person, you give it all the wins, n minus 1 times if you give him the wins, then the total value would get from that person would be n minus 1 n minus 1 into n by 2, or n minus 1 into n minus 2 by 2. Sorry, you start with 0 up till, you would sum up till n minus 2. Okay, so n minus 2 into n minus 2 1 by 2. This would be the total value you would get from that first person whom you assigned all the wins, and for the remaining person they would have all the loss. Whenever you transfer a win from the first person to someone else, that last if you are taking till n minus 1, you are adding from 0 till n minus 2, the last n minus 2 gets taken out and you add a plus 1 to that. So you are basically decreasing the value. So you can like greedily recognize the maximum value you would get is if you assign any one of the person all the wins, all the n minus 1 wins are assigned to one person, and for rest of the n minus 1 people, they are assigned just one loss. They are assigned just loss. In this way, we can just get this maximum value. I hope this is like quite greedily clear to you how we are getting this maximum value. So basically what we can say that the maximum value we would get is just take the first person, make him win against each and every person. So the first time when he wins, you add plus 0. Next time when he wins, you add plus 1. Next time when he wins, you add plus 2. Up till n minus 1th time when he wins, you add n minus 2. So this maximum value would be n minus 2 into n minus 1 by 2. This you can say is our maximum value. You can verify that for n equal to 2, this value is 0. So for first test case, maximum was 0. For n equal to 1, this for n equal to 3, this value was 1 into 2 by 2, which would be 1. So maximum is 1. For n equal to 4, again 2 into 3 by 2 is 3. So maximum was 3. For n equal to 5, 3 into 4 by 2 was 6. So you get 6. Okay, you can verify from the test case. So this is the formula for the maximum that we get. What about the minimum? If you think of the minimum, again, this sequence would still remain. Now you want to minimize this sequence. Okay, so how do you minimize this? So what you would try is maybe every person gets a win and a loss, win and a loss, win and a loss, win and a loss. Like if you assign something like this, and for then every person would get just a plus 1, plus 1, plus 1. So what you are trying to do is maximum you can get from a fight is just plus 1. Or other way to say that is if you have n people, all with 0, 0, 0, 0. Initially try all the 0 and 0s, they all fight together. And okay, or not 0 and 0. Initially try this first person would fight with this 0. You get a quotient of 0. One of them gets eliminated and one of them become 1. And then this person would fight another person and then make this person lose. If you make this person lose, his value would become 1. This person would lose. Make him fight with the other person, make him lose. This value would become 1. This person would lose. So for the first fight, you would get 0. For rest of all the fights, you get plus, you add plus 1 to the answer. This is the like minimum you can get. that for the first fight you get 0, from the second fight onwards you get a 1, and whoever had a skill value of 1, make him lose. Then whoever had a skill of value 0, he becomes 1. Again, when these two fights, whoever had a skill value of 1, make him lose. So every time you would have a fight between 1 and 0. Every time you have a fight between 1 and 0, so from second, third till n minus 1th onwards, you get 1 1 as the value. So the total value you get would be n minus 2. So this is one way to verify. Other way to verify is here for all these n sequences, you assign WL till n minus 2th sequence, and the last sequence you assigned L. Okay, so like this way also, you would add just +1. Sorry, to the first n minus 2 sequence you assign WL. For n minus 1th and nth sequence you assign LL. Okay, this way these would have a 0 0, and first n minus 2 would have 1 1 value. So this way we can say that our minimum is n minus 2 is our minimum. You can verify for n equal to 2, minimum was 0, n equal to 3, minimum was 1, n equal to 4, minimum was 2, n equal to 5, minimum was 3. So our final answer is just print n minus 2 and n minus 2 into n minus 1 by 2. So if we look at the code, our maximum is n minus 1 into n minus 2 by 2, minimum is n minus 2, just print minimum and maximum. I hope this is clear to you. Okay, so if this is clear, I guess we can move to the next problem. So cyclic shift minimization. A permutation P of size n is an array of size n consisting of integers. But why making each time with 0 0 don't give the minimum? Like that way also you would get the minimum. If you think, if you have all the 0 0 zeros, let's say for n equal to 6 you have 6 zeros, you can make 0 0 and 0 0, each of them fight together. For the first 3 fights you get 0, and then you would have 3 of them get eliminated, and for rest of the values you would have 1 1 and 1. And then if you make any 2 of the ones fight, they would add a value of 2, and then whoever loses, the winner, for the winner value becomes 2, and when 2 and 1 fights, 2 plus 1 would give a 3. So in total 2 plus 3 you would get 5. For n equal to 6, through that other way you were getting n minus 2, which was 4. So like this was more optimal, because when you make all the zeros fight, everybody's skill value becomes 1. So when 2 of the ones fight, you add +2 to your answer, and then whoever wins, his value becomes 2. Again you would add +3 to the answer. So these +2 and +3 are like more value getting added to the answer. So that's why this was not very optimal way to do it. So I guess from this test case you can understand that in this way you were getting minimum you were getting was 5, but actually you could have got through the way that I explained, n minus 2, which was 4. So I hope this is clear to you. This was the minimum that you can get. Okay, so let's move to the cyclic shift minimization. So a permutation P of size n is an array of size n consisting of integers from 1 to n, each exactly 1 in some order. Define Fp as the number of fixed points that in number of I says that Pi is equal to I. Okay, so you have a permutation. Now Fp is defined as number of indices in that permutation, so that the value of at the ith index is Pi itself. The is I itself. The value at the ith index is I itself. Now, a cyclic shift of a permutation is, if you shift it cyclically x times, then you start with px plus 1, go up till pn, and then p1 to px. Okay, so if you have a number from p1 to pn, if you cyclically shift it x times, then whatever is the xth index, from here to here you take, and then from p1 up till x minus till x you take. So this way you can like cyclically shift an array. So there would be exactly n types of cyclic shift that you can do. Okay, after you do the n plus 1th cyclic shift, it would come back to the original array only. So that's why there would be n different cyclic shift you get for each value as the first element of the array. You can understand. you get one different cyclic shift. So define GP as the max of f of q over all q which are cyclic shift of p. So function fp was defined as number of fixed points in the permutation p. GP is defined as among all the different cyclic shifts of the permutation p. If you take any of them, whatever fp you get, the maximum among all the cyclic shifts is your GP. So if you cyclic shift it in all the n ways, then among all those n ways, whatever is the maximum value of fp you get, that is your GP. Construct a permutation of size m which has minimum value of GP among all permutations of size n. So among all the permutations of size n, which permutation of size n has the maximum minimum value of GP? So you have to basically minimize the value of GP. You have to just find any one particular permutation having minimum value. Okay, just you have to construct any one permutation. Okay, so this is the problem given to you. Let's look at some of the test cases to understand. So for one, the only permutation possible was one only, so its answer is one only, quite obvious. For n equal to 3 and 6, we can have a look. So for n equal to 3, the number of different permutations possible here was, let's say 1, 2, 3 was one of the permutation possible here. Okay, like there would be 3 factorial permutation, 6 permutations. So 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So these would be the 6 possible permutations. Okay, let's look at the value of GP for all the 6 permutations. So for this permutation, you have to make all the cyclic shifts. So you have to consider 1, 2, 3. One cyclic shift would make it 2, 3, 1. Then the next cyclic shift would make it 3, 1, 2. So for all these cyclic shift, for this, you can see that if you index it, the number of fixed points you get where ai equal to I is 1, 2, 3, all the 3. So for this, your answer is 3. For these, it would be less only. So maximum among them would be 3. So for this permutation, you get 3, the value of GP. For this, you would have 1, 3, 2, which would shift to 3, 2, 1, which would shift to 2, 1, 3. Here 1, 3, 2 would have 1, 2, 3. So one fixed point. So its value would be 1. Here, if you look, you would have 1, 2, 3. So again, one fixed point, this 2. Here you would have 1, 2, 3. So again, one fixed point, 1. So maximum among these 3 is 1. So for this, your answer is 1. Your GP value is 1. For this permutation 2, 1, 3. Okay. Now you can see this 2, 1, 3 comes here only. So this is a cyclic shift of this one only. So when you shift it cyclically, you would get these 3 arrays only. So these two are actually the same. These two permutations returning any of them are actually the same. Both of them are cyclic shift of each other. So their GP value would remain the same. So their GP value would be 1 only. Okay. If you look at this, you have 2, 3, 1. So 2, 3, 1. Cyclic shift it, it becomes 3, 1, 2. Cyclic shift it, it becomes 1, 2, 3. Okay, so this 1, 2, 3 is again same as this. So this cyclic shift and this cyclic shift are actually the same. So for this also, we would have 1 as our answer. Okay. Now, if you look at 3, 1, 2, this cyclic shifted would become 1, 2, 3, again same as this. So all these are same. So for this, our answer was 3. For this also, our answer would be 3. Now, if you look at this 3, 2, 1, this cyclic shifted is actually same as these two arrays. So its answer would be 1. So either if you select any of these 3, your answer would be 3. If you select any of these 3, your answer would be 1. So what is the minimum among them? 1 is the minimum. So in your answer, you would return either of these 3 permutation. You can return either of these 3 permutation as your answer. So the answer returned for this was 2, 1, 3. This was returned as your answer. You can also return 1, 3, 2 and 3, 2, 1. They all are the same. Okay. So we can say that for n equal to 3, the minimum value of the maximum of all the cyclic permutations you got was 1. Okay, and you returned one of the permutations satisfying that minimum value. Let's look at n equal to 2 as well. If you look at n equal to 2, only permutations you can have is 1, 2 and 2, 1. This cyclic shifted is 2, 1 only. So these two permutations are actually the same, and their value for this would be 2 and for this would be 0. So max among the two is 2. So if you pick any of these permutation, the GP value you get would be 2. So you can return any of these. The minimum GP value you can get is 2 because cyclic shifted of them would give at least 2. Okay, so for n equal to 2, this you can say for n equal to 2, our answer was 2. Like the minimum value was 2. You can return a permutation accordingly. For n equal to 3, our answer was 1. Let's look at n equal to 4 as well. If you think of n equal to 4, what permutations you can have? 1, 2, 3, 4. Okay, or maybe. Okay, now think it like this. If you take this permutation, it would definitely have a value of 4. The maximum you take any of, if you, this permutation is giving you a FP value of 4, their cyclic shifts would give less only, so maximum would be 4. If you like cyclic shift all the 4 permutation, those 4 permutations would be the same. What other permutations can you return? So other permutations you can make by swapping any two elements. So if you swap these two, you would get 2, 1, 3, 4. So all the cyclic shifts of this permutation, if you compute the maximum among them, then here you would have 1, 2, 3, 4. So these two are same. So you get a value of 2 from here. If you take cyclic shifts of these, then 1, 3, 4, 2. So 1, 2, 3, 4. Here you get 1 and none of the else as same. If you cyclic shift it, 3, 4, 2, 1, 1, 2, 3, 4, you get 0. If you cyclic shift it, 4, 2, 1, 3, 1, 2, 3, 4, again you get 0. So among these cyclic shifts, here you are getting the maximum value, which was 2. So you can see that whenever, like, if you just look at this 1, 2, 3, 4, this permutation, what different permutations can you create which are not cyclic shift of each other? Okay, so if you look at n equal to 4, you would have 4 factorial permutations, which are 24 permutations. And for every permutation, you would have 3 more cyclic shifts. So you would have groups of 4 permutations, which are cyclic shifts of each other. So the number of different groups you get is actually 6. Only 6 different groups would exist. What else those 6 different groups would be? One group would be for 1, 2, 3, 4. Then just swap any 2 elements. This would be some other group. Let's say you swap some different elements. 4, 3. Okay. So if you swap some different element, that would be some different group. If you swap these 2 elements, this would be different group. So like if you swap any 2 of the elements, you get 6 different groups. Those are actually the 6 different groups that you would get from this. Because if you are making 2 of the swaps, eventually they become the same. Now you can see that, or you can make 2 of the swaps also. Still, whenever you swap 2 values, for this there were 4 permutations which were equal. Whenever you swap 2 values, you can reduce it by 2. Either you would reduce it by 2, or if you swap 2 values, you would increase it by 2. So you can see that for a permutation of size 4, the FP values that you get, would be either 4, 2, 0. These would only be the FP values for n equal to 4. You would never get an odd value. Same way if you try for n equal to 3, as you saw, n equal to 3, we saw here. The FP values that I got for n equal to 3 was 1, 1, 1, 3, 3, 3, only 1 and 3. So if you place 1, 2, 3, you get an FP value of 3, and whenever you swap 2 values, you get an FP value of 1. Same thing we can say for n equal to 4 or 5. If you place 1, 2, 3, 4, 5, the FP value you get would be 5. Whenever you swap 2 values, you may reduce it to 3, you may reduce it to 1, but it would be all odd values only. 1, 3, 5. You would never get even values. For n equal to 6, you would only get even values, 2, 4, 6. So you can say that for whenever n is odd, your FP values are always odd. So the minimum you can reduce your FP value to is 1. Like, you can never make it 0. This is the first proof that can you make GP value? Can you make the GP of any permutation 0? No, because whenever you have a permutation and you cyclically shift it, let's say you have an element X at some index I. When it moves for all the n cyclic shifts, at some point it would eventually come to the index X and give you 1 as your FP value. So always any permutation, if you shift it cyclically, at some point it would at least give you an FP value of 1. So we can say 0 is never our GP value. So it would not happen that all the n cyclic shifts of a permutation give you a value 0. This is impossible because for any element X, if you see, there would be one particular cyclic shift where this X would be at the position X only, which would give you a cyclic shift of 1. Okay. So we can say 0 can't be our answer. So the minimum we can get would be 1. Now for odd, we can say that if we can reduce it to 1, that would only be my minimum. And for n equal to even, we can say that the only FP values we get are 0, 2, 4 even values. So we can never get 1 in this case. So in this case, we can say that the minimum FP value you can make is 0, 2. Minimum GP value you can make is 2. So in odd, we would try to make the GP value 1. In even, we would try to make the GP value 2. If we can do that, that is the most optimal. I hope you would have got the proof. Now, how can we make the GP values for odd equal to 1, for even equal to 2? We have to think of some construction to do that. One of the best way to do that, one of the very good construction here was just take this array. N minus 1, n minus 2 up till 1. Just take this permutation, the reverse permutation. If you take this permutation, just try to think what would be the GP value of this particular permutation. Let's say for n equal to 3, GP value of 3 to 1 was, for the initial this permutation 1, 2, 3, this middle one would give me a FP value of 1. Whenever it moves, here for 3 we had seen for all the permutations that our final answer was for n equal to 3 was 1 among these permutations. So 3 to 1 was actually giving me a GP value of 1. For n equal to 2, you can always take 2, 1, it would give you a GP value of 2. For n equal to 4, let's see. For n equal to 4, if you take 4, 3, 2, 1, what GP value would it have? So 1, 2, 3, 4. Here FP value would be 0. Cyclic shift it. Here FP value is this 1 and this 1. 2 is the FP value. Cyclic shift it. 1, 2, 4, 3. FP value becomes 0 again. Cyclic shift it. 1, 4, 3, 2. FP value becomes 2 again. So all the 4 cyclic shifts, among them the maximum was 2. So for n equal to 4 also we can say that this reverse permutation works. For n equal to 5, let's try. 5, 4, 3, 2, 1. Cyclics, here you get a FP value of 1. Cyclic shift it. 4, 3, 2, 1, 5. FP value that you get is this one. Cyclic shift it. 3, 2, 1, 5, 4. FP value you get here was this as 1. Then again you can see like for 5 also you would get an FP value of 1 and 1 only. Now if I want to prove that always this works, then whenever you take a permutation from n to 1 and whatever cyclic shift you do, after doing a cyclic shift the permutation would become start from some x, go on till 1, and then start from n, go until x minus 1. This would be any cyclic shift for any x of this reverse permutation. Now here we can say that if you start the indexing from 1, 2, 3, 4 up till n, when would this value merge with the index? So this x becomes equal to 1. This is not happening. This indexes is increasing from 1 to n. So basically these indexes are increasing from 1 to n, values are decreasing. So if you like merge them into a single graph only, then at one point these two would merge, this would be the one value would get, and at one point these two would merge. So at max here we can say that we can have two points where pi is equal to I. And for odd we have already proved that for odd we would never have a fp of 2. This is not possible. So for odd at max it would be 1 only. So we can say that like this, we can prove that if you just take a permutation n minus 1 up till 1, this would always be right. For odd it would give you a GP value of 1, for even it would give you a GP value of 2. Okay, so is this logic clear? So if this is clear to you, code would be like quite simple. Just start with I equal to n to 1, print all of them space separated, see out max lesson. Oh, this is the code. Its time complexity is for printing running a loop of n. You get order of n time complexity. Space complexity is order of 1. You are not using anything other than an intel. Okay, so I hope this problem is clear to you. Any doubts in this problem? So I guess we can move to the next problem. So the next problem is min steps. So you start with integer x equal to 1. In each step, you can do exactly one of the following: x by 2 or add d to x. Find the minimum steps to make x equal to 1. If it is impossible, print minus 1 instead. Okay, so n and d are up till 10 to the power 18. So you cannot do something like order of n, order of d, anything like that. You have to think of some direct approach. So, okay. So basically this is the problem. You start with x equal to 1 and you have two types of operation. Either multiply whatever x currently you have by 2 or add a constant d to x. Now d is fixed for every test case. You have to find minimum steps to reach x equal to n, and if it is impossible, print minus 1. So let's look at some of the test case. Let's say you look at this first test case only, 6-2. So you have here n is equal to 6, d is equal to 2. Okay, so for this we start with x equal to 1. Okay, we start with x equal to 1. We have to reach 6, and the operations allowed to you is whatever x you have, multiply it by 2 or add a plus d. These are the two operations allowed to you. So in this case, what you can do is, let's say you have x equal to 1, you add a plus 2 to this x, you go to x equal to 3. Then let's say you multiply it by 2, you get to x equal to 6. So in 2 steps you have reached x equal to 6, and it was not possible to reach here in 1 step. If you add plus 2 to x, you would reach 3. If you multiply it by 2, you would reach 2. You cannot reach it in 1 step. So 2 is the minimum number of steps you would require to reach 6. So here your answer was 2. For 4, 3, if you have n equal to 4, d is equal to 3, what you can do, you start with x equal to 1, you do a plus d, you reach x equal to 4. So in 1 step only you are reaching, so our answer is 1. Okay, let's look at, so 6, 3, If you look at 6, 3, so n equal to 6, d is equal to 3. So if you start with x equal to 1, you want to reach 6. So let's say you do a plus 3, you reach 4. Now you, if you do plus 3, you reach 7. If you multiply by 2, you reach ahead, you reach more than 6. So this was not valid. So maybe you multiply it by 2, you reach x equal to 2. Now from x equal to 2, you want to reach 6. Either you multiply it by 2 and reach x equal to 4, from where again you cannot reach 6, or you add a plus d. So if you add a plus 3, you reach x equal to 5. From x equal to 5, again you cannot reach 6. Either you add plus 3 or multiply by 2. So here we can say that reaching 6 was not possible, whatever you do here. So for this test case, we can say our answer was -1. Reaching 6 is not possible. So likewise, you have to answer each test case, the minimum number of ways to reach n. Okay, so how do you solve this problem? So if you look at the problem, you start with x equal to 1. Okay, the only steps available to you is either multiply by 2 or add a plus d, where d is some constant. Okay, so if let's say you add d some, the operations you perform, let's say you perform a plus d operation, then again a plus d operation, then again a plus d operation, then a multiply by 2 operation, multiply by 2 operation, then again plus d operation. Something like that would be the sequence of operations that you perform. Whatever sequence of operation that you perform, if you just look at that sequence, initially you do the plus d operation, let's say x1 times or y1 times. Let's say y1 times you do this operation. Your value after this would become x plus y1 times d. Okay, then if you do the into 2 operation, your value would become 2x plus 2y1 times d. Again, if let's say you do multiply by 2 operation, your x value becomes 4x plus 4 times y1d. Again, if you do some plus d operation, let's say y2 times, it becomes 4x plus 4y1d plus y2 times d. Okay, again, if you do multiply it by 2, it would become 8x plus 8y1d plus 2y2d, something like that. So what final value are you getting? If you look at this first constant value, this would be the, basically you start with 1, and then if you are multiplying or if you are adding some d here, the number of times you are adding d would be the coefficient of d and then some constant value. And whenever you multiply, this constant would get multiplied by 2, and this for d, this coefficient of d gets multiplied by 2. So always your expression is of the form some constant value. This would be some constant value plus d multiplied by some coefficient of d. Okay, let's say this coefficient of d is some constant c1 and this c2 is the coefficient of d. So what would be the values of these two constants, c1 and c2? Whenever you, so if you start with 1, x equal to 1 can be represented as c1 equal to 1, c2 equal to 0. So 1 plus 0 times x, 0 times d. You can say this is 1 plus 0 times d. Whenever you multiply by 2, both the constants get multiplied by 2. 2 plus 0 times d. So c1 becomes 2, this becomes 0. So basically you start with c1 equal to 0, c1 equal to 1, c2 equal to 0. For a into 2 operation, both c1 receives 2 into c1, c2 receives 2 into c2, and for a plus d operation, we do c2 plus plus, just c2 receives a plus 1, c1 remains the same. So you can say that finally what you want to achieve is n should become of the form c1 plus c2 times d, and c1 would be the number of times. C1 would be, you start with c1 equal to 1, only when you perform the multiply by 2 operation, this c1 becomes double, c1 gets double. Whenever you do the plus d operation, there is no effect in c1. So you can say that c1 definitely has to be some 2 to the power I. If you don't perform any multiply by 2 operations, C1 would be 1. If you perform once, C2 would be 2. If you perform twice, C1 would be 2. If you perform twice, C1 would be 4. So here it's 2 to the power 0, 2 to the power 1, 2 to the power 1, 2 to the power 2. So you can say that C1 is 2 to the power I, where I is the number of into 2 operations performed. This thing, if I hope it is clear to you, then we can proceed forward. That even if you look at the, even if you intuitively look how the operations are getting performed, then whatever one you start with, if you start with this x equal to 1, this constant would be just getting multiplied by 2. You started with x equal to 1, it would, whenever you multiply by 2, that 1 would get multiplied by 2, and it would have some 2 to the power I value, the value of that constant. And for the remaining part, whenever you add a plus d, the coefficient of d, this C2, the coefficient of d, this gets multiplied by 2 whenever you multiply by 2, and whenever you add a plus d, this coefficient gets increased by 1. So you can say that your, at any point of time, your x would be of the form C1 plus C2 times d, where C1 is the number of 2 to the power number of times you have performed operation 2. And what would be C2? That we would see accordingly. So if this thing is clear, just write a yes in the chat. Okay, I'll explain it again once. Let's say what I'm telling you, start with x equal to 1. Okay, so the operations available to you is multiply by 2, add a plus d. So whatever number you get, let's say you multiply by 2, you get 2. Again you multiply by 2, you get 4. Let's say you add plus d, you get 4 plus d. You add plus d, you get 4 plus 2d. You multiply by 2, you get 8 plus 4d. Add plus d, you get 8 plus 5d. Something like that. At any point of time, the value you would have, we can say that it would always be some constant plus some coefficient of d. Your value of x would always be some constant plus some another constant times d for any fixed d, depending on what operation you are performing. It would always be of this form. So for every unique value of C1 and C2, it would be a different x. So we can say that when you have x equal to 1, x equal to 1 can be written as 1 plus 0 times d. So you can say that you start with C1 equal to 1 and C2 equal to 0. This is your starting coefficients, 1 plus 0 times d, C1 equal to 1, C2 equal to 0. This is the coefficients you start with. So if any point of time you have C1 plus C2 times d, and when you multiply it by 2, what you get? You get 2 times C1 plus 2 times C2d. That means you can say that when you multiply by 2, you can say that your new C1 is 2 times the old C1, and your new C2 is 2 times the old C2. If this thing is clear, okay, then other way to do that is do a plus d. Other operation you have is do a plus d. Whenever you do a plus d operation, what you get is from C1 plus C2 times d, you get C1 plus C2 plus 1 times d. So here you can say that your new C1 is same as the old C1, but your new C2 is the old C2 plus 1. So looking at this, you can say that always if you start with the pair of C1, C2 as 1, 0, then in every operation 1, both of them doubles, both the coefficient doubles, but in operation 2, the second coefficient increases by 1, first coefficient remains the same. So if I'm telling that you have, let's say, y number of into 2 operations, and z number of plus d operations, then what you can conclude about C1 and C2? So C1 is only changing with into 2 operations. So whenever you get an into 2 operation, you start with C1 equal to 1. Whenever you get an into 2 operation, it doubles. So with y number of operation 2, you can say that your value of C1 would be 2 to the power y. For each into 2 operation, your C1 doubles, and for y number of operations, your C1 becomes 2 to the power y. And your C2 would be, now your C2 may vary here, that for any into 2 operation it would double, but for plus d operation it would increase by 1. So this, like, currently you cannot predict this. You would need the order of when the multiply by 2 operation is performed and when the plus d operation is performed. If the order is given to you, then only you can calculate the exact C2, but C1 you can calculate exactly as 2 to the power y. If this thing is clear, can we move ahead? Okay, so if till here it is clear, then we can say that your this constant value would be the number of times you perform multiply by 2 operation. Now, you know for sure what you finally want to achieve. You want to achieve C1 plus C2 times D to be equal to N. This is the value you want to achieve finally. So now we know this both C1 and C2 would be greater than 0 only. These would be positive values only. So what can be the all possible values of y you can have in your answer? At max, how many multiply by 2 operations you would perform? Since it is increasing exponentially with the power of 2, so the range of n given to us is till 10 to the power 18. So if let's say we take y is equal to 60, then 2 to the power 60 would reach something of the order of 10 to the power 18. So at max, the number of type 1 operations, the multiply by 2 operations, at max you would perform is 60. You would never perform more than 60 times. If you perform more than 60 times, this C1 would exceed 10 to the power 18. If C1 exceeds 10 to the power 18, that means you have already exceeded n. So you can basically iterate over this y. That's what I'm trying to say. That if you fix the number of type 2 operations, type 1 operation, multiply by 2 operations, if you fix the number of multiplication of operations, then you try to just minimize your total operations, just minimize this z. If you fix the y and then try to minimize z for every y, that way also you can minimize the overall answer. Your final answer that you want to minimize is y plus z, total number of operations. So fix this y. This y may vary from the range 0 to 60. Okay, so order of 60 is fine. So every time you fix your y and then try to compute what is the minimum z you can have for y. Okay, so now what I'm telling, that I have fixed that, let's say I is the number of type 2 operations, type 1 operations, which is multiply by 2, that we are performing. We have fixed this as the number of type 2 operations that we are performing is fixed to I. So once we have fixed this, now let's try to minimize the number of type 2 operations plus d operations that we get. So now my value of C1 is 2 to the power I. So what we want to achieve is n is equal to C1 plus C2 times d. So this can be replaced by 2 to the power I. So what we want to achieve is C2 times d should be equal to n minus 2 to the power I. So first of all, this C2 is an integer. So this should be divisible by d. If it is not divisible by d, then this is not possible. Directly you can say for that particular I, it is not possible to reach n. So first check you would have that whether this is divisible by d. If this is divisible by d, your C2 should be n minus 2 to the power I upon d. This is the C2 that you want to achieve using I number of type 1 operations and minimum number of type 2 operations. Now this is fixed for any fixed I. For fixed I, n minus 2 to the power I by d, this whole thing is a constant. Let's say this constant is some x. Okay, let's say this constant is some x. So then, okay, x was the initial value. Let's take it y only, like, okay, just take it any variable. Don't confuse it with the initial y that I was taking. That is taken as I here. Okay, so let's say you want to reach C2 is equal to y, or we were taking z only, na? Let's take it z only. Let's take it z only. Okay, so you wanted to have z number of type 2 operations, or C2, so that is not z. Okay, this is some constant. This is some constant k, let's say. Okay? So you want to reach C2 is equal to k. This can be calculated as n minus 2 to the power I by d using I number of type 1 operations. So you start with C2 equal to 0. Your initial C2 is 0. Whenever you perform, now what is happening? Whenever you perform a type 1 operation into 2 operation, you do C2 as 2 into C2. And whenever you perform a plus D operation, you do C2 plus plus. So you are either multiplying it by 2 or adding a plus 1. So if you look at this C2 in binary, like multiplying by 2 is actually left shift 1. Adding a plus 1 is just adding a plus 1 to the starting bit. So if you look at this C2 in binary, then you start with 0. Okay. Whenever you multiply by 2 initially with 0, there's no effect. But whenever you add a plus plus, so whenever you do the second type of operation, you change the first bit to 1. Then if you do the first type of operation, you would shift it right, and this value would become 1 0. Then if you add a plus 1, this value would become 1 1. Then if you shift it left, this value would become, okay. Then again if you shift it left, this value becomes this. Then again if you add a plus 1, this value becomes, okay. So you can see that you are actually moving in binary, that whenever you want to do, you want to form some, finally what you want is the final C2 should become equal to k, this k. So if you represent this k in binary, whatever k you have, let's represent that k in binary. So whatever k you get in binary, you can always reach that k, and the minimum number of operations to reach that k would be, if you want to reach here, start with the first one. You have a 1, do a type 2 operation, plus d operation. So basically a plus 1, it would effectively be plus 1 here. So do a plus 1. So start with 0 0 0 0 0 0. Do a plus 1, it becomes 1. Shift it right. Again you have a 1. So after shifting right, it becomes this. Do a plus 1. So okay, you do a plus 1, it becomes this. Shift it right. After shifting it right, it becomes 1 0. Again do a plus 1, it becomes 1 1. Again you have a 0, so shift it right. When you shift it right, it becomes 1 1 0. You want to keep it 0, so shift it right again. If you shift it right again, you get 1 1 0 0. Again 1 1 0, you want to add 1, so add a plus 1, make it 1. Then you have a 1, so shift it right, add a plus 1. Shift it right, add a plus 1. You want to have a 0, shift it, just shift it right. Then have a 1, shift it right, add a plus 1. So this way, hope you can get that you can always get to any binary value of that k using these left shift and a plus 1 operations. You can always get to any binary value. And this will always be the minimum number of operations. You would ask why? Then whenever you are doing a left shift operation, like you are doubling the values, so this same effect can be done through second type of operations by, if you have, let's say, x equal to 6, you do a multiply by 2 operation, you directly make it 12. But using a type 2 operation, you would have to add a plus 1 6 times to make it 12. So instead of using these 6 operations, you use 1 into 2 operation, it would double and become that. So like if you think in binary, this is the best way to do minimum, most optimized or optimal way to do that. Okay. Once this thing is clear, now still here it is clear. Plus 1q, as I explained already, that the C2 I am considering is the coefficient of D, not the D itself. So my number is of the form C1 plus C2 times D. So whenever I do plus D, in the coefficient I am doing plus 1 only. So in the coefficient of D I am doing only plus 1, not a plus D. So doing a plus D is effectively doing a plus 1 to the coefficient of D. So I have reduced my problem to, instead of finding minimum ways to reach n, since I am fixing my I, so n minus 2 to the power I is n minus 2 to the power I is C2 times D, divided by D is C2 actually. So I want to reach actually C2 is equal to n minus 2 to the power I minus D. So if I want to reach this particular value of C2, to reach here, if I do the first operation, this C2 would get multiplied by 2. If I do the second operation, this C2 would increase by 1. Okay. So I'm looking at the coefficient of D, which I want to make as K, which is this constant thing. Okay. So I hope now it is clear. Okay. So if till here it is clear, now there is one small issue with this thing, that let's say I'm telling that the minimum number of ways to reach here is whatever is the highest bit, that many times you would have to do a left shift, and how many times you have one, that many times you would have to do a plus 1 operation. So for this we can say that the minimum number of operations is number of ones in this binary representation plus, you can say, MSB, the highest significant bit, that many left shifts would be required. But while before doing this, we had fixed the number of type 1 operations to I. We had fixed that I is actually our number of type 1 operations. So if I'm telling that its MSB is, let's say we have fixed I is equal to 5, that means I can only do the multiply by 2 operations 5 times in this particular case. And here, if you see, to reach this one, you would have to do a left shift of 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 8 left shift from 0 to index 8. If you index it 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if you start with this one from here, you would have to left shift it 8 times. So the minimum that I was talking about here was the number of ones here was 1, 2, 3, 4, 5, 6. So 6 number of type 2 operations and 8 number of type 1 operations. This way it would be minimum. But here I had fixed I equal to 5. I was calculating for a fixed I equal to 5. So I cannot do more than 5 type 2 operations. So I can only do 5 type 2 operations. So till 5, till here, I can make this complete binary representation. But in order to bring a 1 in these positions, I don't have a type 2 operation, a type 1 operation, the multiply by 2 multiplication operation. So I can have a 1 here only by using a plus 1, the second type of operation. So what is the minimum second type of operation required for this type of case where this I is less than the MSB? So when I is less than the MSB, what we can say in minimum, how many operations of type 2 we can do this? So in order to get a 1 here, if we have a 1 here, we can do a plus. If we do a plus 1 here, so let's take smaller test case only. Let's say I is 3 and you want to reach K is equal to 0, 1, 1, 0, 1, something like 0, 1, 2, 3, and let's say 0 here. Okay, let's say I is 3. So you can do only through left shift operations, you can make this particular number, but you cannot get a 1 here, because in order to reach a 1 here, starting from here, you would have to do 4 left shift operations. So what you can do here is, in order to reach here, if you do a plus, what we can do is we can start with, if you start with this C2 is equal to 0. Now, in order to reach here, in 4 left shift operations only, we can reach a total of 1 1 initially using a plus 1 operation only. Let's say how you do a plus 1 here, you reach 0 1. Again, if you do a plus 1 in this only, you get 1 0. Again, if you do a plus 1 in this only, you get 1 1. So using 3 plus 1 operations, you have got 1 1 without doing any left shift operation. Then you do a left shift operation. You do a left shift operation, you reach 1 1 0. Then you do a plus 1 operation, you reach 1 1 1. Then a left shift operation, you reach 1 1 1 0. Okay, you have reached this 1 1 1 0. Then again do a left shift operation, 1 1 1 0 0. Then do a plus 1 operation, you reach 1 1 1 0 1. 1 1 1 0 1. This final string you have obtained now using only 1 2 and 3 left shift operations. So here, if you had 4 left shift operations, you would have done it using 4 left shift operation and 1 2 3 4 plus 1 operation. But since you only had 3 left shift operation, number of plus 1 operations required were 1 2 3 4 5. So 5 plus 1 operations were required instead of 4. So what you can say, that how do you compute the minimum is, till here for the first I indices, you can always form this. For this particular index, what you can say, that you are doing a plus 1 here. Whenever this one was at the 0th index, that time you do some extra plus 1. So if you do 2 times extra plus 1 here, those 2 plus 1 would contribute to a plus 1 at this index. So you can add a plus 1 at this index by doing 2 times plus 1. So this we can say that apart from the first I indices, for rest of the indices, whenever you get a plus 1, whenever you have a bit value 1, it would contribute to your, as if you are doing plus 1 here. So if it is I distance away, you would have to do 2 to the power I times plus 1. So if it was 1 distance away, or not I, if it is j distance away, let's say this is index j, so and this is index I, so you would have to apply a operation 2 to the power j minus I times. The second operation need to be applied 2 to the power j minus I times. Here you can say, for this second operation needed to be applied 2 to the power 4, 2 to the power 4 minus 3, which is 2 to the power 1 times. So 2 times first operation was required to be performed in order to do a plus 1 here. So for the first I indices, every one would contribute a plus 1 to the second operation. For the remaining, a 1 would contribute 2 to the power j minus I to the number of type 2 operations. This way you can get the minimum number of type 2 operations. And once you get the minimum number of type 2 operations, for every I, minimize the number of type 2 operations and minimize the overall type 1 plus type 2 operations. This way you will minimize the overall answer. Is this thing clear to you? If this thing is not clear, another way to do it is, if you look at this number, then what I can say, that before every multiply by 2 operation, let's say you have y1 number of plus d operation. Okay, this is another way to understand this. Then again you have a type 2 operation, then y2 number of plus d operation, y3 number of plus 2 operation. So if you have I number of multiply by 2 operations, then you would have from y1, y2 up till y, these I would divide it into I plus 1 groups. So y I plus 1. Okay, so these would be there, and before the first type 2 operation, whenever you do plus y1, your C2 would become y1. After the first type 2 operation, C2 becomes 2 times y1. Next plus d operations 2 times y2, then up into 2 operations makes it, okay, then into 2 operation multiply by 2, it makes it 4 times y1 plus 2 times y2, then plus y3 you get. So this way if you see, your C2 value would be, this y1 would get multiplied by 2 times, so y1 into 2 to the power I, y2 into 2 to the power, this y2 would get multiplied I minus 2 times into 2 to the power I minus 1 times, plus up till y plus 1 multiplied by 2 to the power I times. So this would be multiplied by 0 times. Okay. So you have to find some particular array y with minimum value of the sum of array y to satisfy this thing to be is equal to k. So basically you can see all these coefficients are some powers of 2 from 0 to I. So basically in binary you can say, again in binary from 0 to I, you can do a plus 1 to any of the powers of 2. Whenever you do a plus 1 here, you are doing a plus 1 to y0 or y1 here. Whenever you are doing plus 1 to this bit, you are doing a plus 1 to y2. Okay. Now you are restricted till ith bit only. So if you want to do a plus 1 in this bit, if you want to do a plus 1 in this bit, you can do 2 times plus 1 in this bit to make a plus 1 here. Or if you do 4 times plus 1 here, you get a plus 1 here. Or if you do 8 times plus 1 here, you get a plus 1 here. So basically you do j minus 2 to the power j minus I times plus 1 to get a plus 1 at the jth position if j is greater than I. Okay. So if this logic is fine to you, we can move to the code. So if you look at the code, I initialize my minimum value with some infinity. If it remains infinity, I'll print -1. Okay, so infinity is 218. Okay, I iterate through all the possible values of I from 0 to 60. Okay, so every time I'll fix that the number of type 1 operations is I. Okay, so if I fix the number of type 1 operations, the k that I was trying to find, my answer was n minus 2 to the power I. So n minus 2 to the power I have taken that as x, and if this thing becomes less than 0, then obviously we would break, because if 2 to the power I becomes greater than n, then we are finding for some negative value, which we would not do. C2 can never become negative, so we would break there. We would not proceed to further higher i's, which would even decrease this lower, so we would break there. If x is not divisible by d, so if this particular thing is not divisible by 3, then this case cannot be considered. We would skip this I, we'll put a continue, skip this particular I, try for the next I. If it is divisible, then our k would be n minus 2 to the power I by d. So if x becomes 0, okay, so if this thing becomes 0 only, that means C2 is 0 initially only, no type 2 operations are required. So in I number of type 1 operations, we can do this. So this we can say is our minimum value. This we would minimize and break out. After that, with an increased value of I, this would become 0, so break out. Other than that, if you don't break or continue, that means this n minus 2 to the power I divisible by d. So this divided by d, what we get is our k. So here I have taken that as y, okay, x by d. So the y in my code is the k that I explained here. Now I want to make y. I want to make y. So I want to make this k using minimum number of type 2 operations. So I'll iterate through all the positions from 0 to 60. I'll iterate through all the bits of y. So starting from j equal to 0 to 60, if y and left shift j. So if the jth bit of y is set, okay, so whichever bit is set, it would contribute something to the answer. If this jth bit is less than I or even equal to I, that means we are in the first I bits, then it would add a +1 to the answer. So if j is less than equal to I, just answer plus plus. Otherwise, if j is greater than I, then answer plus equal to 2 to the power j minus I. 2 to the power j minus I. So once we have done that, then we get the final answer, which we are initialized with I. So I number of type 1 operations, and this way we update the number of type 2 operations. So in answer, we get the total number of operations for this fixed I. This we minimize with the minimum overall answer. If the minimum of overall answer remains infinity, we print -1, otherwise we print the minimum answer. Okay. So I hope this logic is fine to you. Okay. So if this logic is clear, we can analyze the time complexity. This is running 60 times. These are O of 1 things. This is also running 60 times. So this is running 60 into 60 times. So this we can say is running 60 into 60 times. And these are O of 1. So time complexity is order of, where 60 was actually log of n. If you look at the problem statement, n was given up till 10 to the power 18. So log of 118 was 60. That's why we took 60 here. So whatever was log of n, that was our time complexity. Square of log of n, square of 60. And space complexity would be, we are just using these variables, nothing else. So order of 1 space, no extra space required. Okay. So I hope this problem is clear to you. Any doubts in this problem, please ask. So shall we move to the next problem? Yeah, this like requires, if you have intuitive feel of solving a lot of bit manipulation type of problems, then this would like come to you like intuitively if you have solved many problems of bit manipulation. But if you have not solved a problem, then you would always ask the question, how did you think like this? Okay. So like whenever you have some constraints like 118 and all, you know for sure that you cannot iterate through all them. So you'd have to think something in binary or in the digits of that. So either you'll apply some, now make applying something in the digits of n was not making any sense, because the operations available to us was multiply by 2 and plus 1. So we converted those operations into binary, that multiply by 2 is actually a left shift operation. So if you think like that, if whenever you get something like multiply by 2 type of thing, you can always think it like a left shift operation. And when you think in binary, you would like get what actually is happening here. So if you thinking in binary is like very, was the sole way to solving such problems, and you would have to practice a lot of problems in order to get this intuition. Okay. CF equivalent rating, I don't know, maybe 1700 types, 1600 types, probably, not sure. Okay, I guess let's move to the next problem. So the next problem is, an array A of length n is good if the product of the array is equal to the sum of the array. That is, product equals sum. Now, given an array A of length n, count how many subarrays of A are good. Formally find the number of pairs L and R such that, basically, how many subarrays are good. That's what you need to find. So the n is given up till 2 into 10 to the power 5. So you cannot check individually for every subarray, because there can be n square number of subarrays and order of n square would not be accepted. This is the first thing to notice in the problem. Otherwise, taking some prefix sum and prefix product and checking for every subarray was fine, doing it in order of n square, but that you cannot do. Okay, so you'll have to think some clever way to do that. Okay, let's look at one test case to understand the problem if you haven't already. So if you look at this test case, let's say you have this. So you are given an array. You want to check that how many subarrays satisfied the condition that sum is equal to product. So let's check for every subarray. 0, 1, 2, 3, 4, 5. Let's index it. Let's check for this. Any subarray of size 1, if it has only one element, its sum would be AI, its product would be AI. So they would be equal for sure. So these 6 single element subarrays would add to the answer for sure. Okay, they would be my answer for sure. Okay. Other than that, for at least two sized sub-arrays, 1, 2. If you check this, its product is 2, its sum is 3. So 2 is not equal to 3. Product and sum are not equal. So this is not valid. Okay. Let's check for 2, 1. Again, 2, 1 not valid. Product is 2, sum is 3. Let's check for 1, 4. Product is, sum is 5, product is 4. Again, not equal. Let's check for 4 and 1. Again, 4 and 1, sum is 5, product is 4. 1 and 1, sum is 2, product is 1. Not valid. So two-sized subarrays, none of them were valid. Let's check for three-sized subarrays. If you check for this, the sum is 4, product is also 2 into 1 into 1, it's 2. Again, 4 is not equal to 2. This is not valid. If you check for this particular subarray, sum is 2 plus 1 plus 4, 7, product is 8. 7 not equal to 8. Not valid again. If you check this subarray, sum is 6, product is 4. Not valid. If you check this subarray, sum is 6, product is 4. Not valid. Okay, let's check this particular subarray. The sum is 2 plus 1 plus 1 plus 4, which makes 8. Product is 2 into 1 into 1 into 4, 8. Product and sum are equal. So this subarray is valid. So plus 1 to the answer. Okay. Next, let's check for this particular subarray. Again, 2 plus 1 plus 4 plus 1, sum is 8, product is also 8. This is also valid. Again, a plus 1 to the answer. Okay, let's check for this subarray. Sum is 7, product is 4. 7 not equal to 4. Not valid. Let's check for subarrays of size 5. So for this subarray, sum is 3, 2, 5, 4, 9, product is 8, unequal. And if you check for this subarray, again, it's the same. Sum is 9, product is 8, not equal. If you check for the whole array, sum is 4, 4, 8, and 2, 10, product is 8. 10 not equal to 8, not valid. So the total number of valid subarrays you got here was 6 single subarrays and plus 1, 2 other 4-sided subarrays that you got. So in total 8 you can say is the number of valid subarrays for this test case. 8 was our answer. Okay, I hope you would have got what the problem is asking you to do. So if the problem was that n square was allowed, then it was pretty easy. Check for every subarray their sum and product using some prefix array and prefix product. You can just calculate the sum and product of any subarray in order of 1, and then you can check for all subarrays, but number of subarrays are n square. So this thing would not be valid. So how can you do it in order of n? So let's try to think. When would it happen that sum would be equal to product? What is the case? So in general, if you like think that if you have many numbers, all are positive numbers, sum would like definitely in most cases would be less than their product. If you're multiplying some numbers, it would like very fast become very large, and adding some would be small. Now, when can we generalize this thing that the sum is less than equal to product? If you try to think, when would be the cases when sum would be equal to product or sum is greater than product? For what values? And when we can say that this is the product is definitely greater than the sum? Just try to answer this thing. How can we like, for what values of the array and how many values of the array you can like generalize this thing that sum is less than product? So if you like take some big values, let's say if you take some 3 and 4, the sum would be 3 plus 4, product 3 into 4 would definitely be greater. If you take something like 2 plus 2, the sum is 4, product of 2 plus 2 is also 4. 2 plus 2 is one like peculiar case where sum and product are same. But other than that, if you take 2 plus 3, sum is 5, 2 into 3, product is 6. This is still greater. So But if you take 1, whenever you add a plus 1, you are increasing the sum. But when you are multiplying by 1, the product remains the same. So if you ignore the ones, let's say you have all the values of the AI are greater than 1. All positive values like greater than 1, integers greater than 1, that is greater than equal to 2. Then we can we always say that it would never happen that sum becomes greater than product? Can it happen? If you just remove all the ones from the sequence, then can it ever happen that sum is greater than product? When having ones, then sum could become greater than product, else sum would always be less than, mostly except 2. Okay. So exactly. When you ignore all the ones, then you can always say that definitely sum is less than equal to product. And even this equality is satisfied only for one case, 2 plus 2 equal to 2 into 2. Except this case, for any other case, we can just say strictly the sum is less than product. So what is the proof for that? Like, also I'm considering that at least I'm taking at least two numbers. For one number, always sum is equal to product. There's just one number. So I'm taking at least two numbers. Then we can say when we are taking at least two numbers, if both the numbers are not 2, then sum is strictly less than product. So for 2 plus 2 is equal to 2 into 2, you know. But other than that, whenever you have a 2 with some value greater than 2, then this product would be, and you take 2, you compare it with 2 with that x which is greater than 2, then in that x you are adding plus 2, it is x plus 2, and here in that x you are multiplying by 2, that means you are making it x plus x. This is 2 plus x, this is x plus x. Definitely this would be greater since I'm considering x is greater than 2. I've already taken one of the two, the second one is not a 2. And if I'm taking both of them greater than 2, then x into y and x plus y. So whatever, if you're starting with x, you multiply by y, where y is greater than equal to 3, that means at least you are adding x 3 times or more only, and here you are adding y to x. So you know, like, this thing would be greater than y. This thing gets cancelled out, and adding this x y times y minus 1 times is greater than the y itself, since x is greater than 2. So even if x is 2, it would be 2y at least. Okay, so this thing I hope you can prove that sum would always be strictly less than product, provided that ai is greater than equal to 2, number of elements in the sequence we are considering is greater than 2. Only one exception is 2 plus 2 is equal to 2 into 2. This is just one exception. Okay, or we can, let's say, less than equal only. Okay, now we have to consider these ones as well. We have to consider these ones in this in between in the sequence as well. So now if you want to check that in the array, if you take any subarray of this, if you want to check in this subarray whether this subarray has sum equal to product or not, or which subarray has sum equal to product, if you look at all the values which are greater than 1, so the product of all those values which are greater than 1, for them the product would be greater than equal to sum. How can you make the product reach equal to sum? By using 1. So whenever you add a 1 into the sequence, what you are actually doing is you are doing sum plus plus, and product remains the same. So if you have in the sequence, let's say, a 3 and a 4, then the product of 3 into 4 is 12, the sum of 3 plus 4 is 7. In order to make the sum and product equal, their difference is 5, so you would have to add 1 5 times to make this sum, add a plus 5 to this sum and the product would not get affected. So you would say that if in this range, whatever is the product of greater than one values minus the sum of greater than one values, whatever is that difference of product minus sum, where we are considering the product of values greater than one, sum of values greater than one, then if you add that many times one in the sequence, then your sum and product would become equal. If this logic is fine to you. Okay. If this thing is fine to you, then how do you solve the problem now? So how does that reduces our problem? Even now we would have to count that for every subarray we would have to check, even if we calculate the product and sum of non-one elements and the count of one, still you would have to check for every subarray. But what I'm claiming now is you would not have to check for every subarray. Why? So now what are the different subarrays that exist in an array? You fix a L. Let's say you fix your L here. You fix the starting element of the subarray, and then you iterate through all the R. So you fix your R here only, then only one element. Then you fix your R here. This is one subarray, this is one subarray, this is one subarray, this is one subarray. Now let's try to compute for every fixed L. You iterate through every L. Now when you have fixed your L, for all the different subarrays that you get in the array, for all the different R that you get in the array, till where would you have to iterate in your R in order to get sum equal to product subarrays? So now what I'm telling is you are just iterating through, okay, whenever you have ones in the array, just ignore them, iterate through all the greater than one elements. Okay, so let's say this element was greater than one, this element was greater than one, this element was greater than one, and in between you have some ones, some ones, etc. So when you iterate through to this R, so in this subarray, let's say you consider, for this subarray, let's say you find that what is the product of this particular subarray considering all the greater than one elements and sum considering all the greater than one elements, and then in between how many ones you have. Okay, so if you are just iterating through the next non one element, then if you know the indexes that where I had the previous non one element, in between all the elements would be one. So in the count of ones, you can just add that many, that size of how many values you skipped in between to the number of ones. That way you can say that if like I am computing for this subarray, let's say till I have iterated my R till here, then till this I would have some product P representing the product of all the elements greater than one, and some S representing the sum of all elements greater than one, and I would also have the count of ones currently. So if the current count of one inside this range, so if this P would definitely be greater than equal to S. If D is the difference between P minus S and the current count of ones in between is less than D, then whatever is, if let's say the product is, if let's say I have a 3 here, 2 here and 3 here, the product would be 3, 3, 9, 18, and the sum would be 3 plus 3, 6 plus 2, 8. So the difference I would get here would be 18 minus 8 equal to 10. Okay, let's say in between I have some 5 ones here and 1 here, so 6 ones I already have, but you need 10 number of ones. So 10 minus 6, 4 more ones are required. So I'll try to extend this R ahead 4 steps. If the next 4 steps there are all ones in the next 4 steps, then I can extend this R 4 steps ahead, and I can say that this range gives me P equal to S. I can add a +1 to my answer. And if I, before extending it to R plus 4, only if I find some element which is greater than 1, then I can say that it is not possible to extend it to get sum equal. Whenever I get greater than 1 element, again the product would increase. So I'll iterate to next greater than 1 element and try to again calculate the new PNS, the new difference, and try to compute how many steps ahead again we would have to move in order to get P equal to S. So what I'm doing is I'm iterating through only the greater than 1 elements. Okay. So in the worst case, how many different R I would have to iterate through? If you think. So in worst case, maybe all elements are, let's say, greater than 1. Or maybe most elements are like majority elements, or most elements are greater. In out of n, even if n by 2 elements are greater than 1, then order of n by 2 square is still order of n square only. It would still give me TLE. So now, how do you optimize this further? So if I'm telling that there are many elements which are greater than 1, then after some point, the product that I'm calculating, it would increase to some very great extent such that it is not catchable. Like if let's say I have 20 numbers which are all greater than 1. So at minimum, they would be 2 to the power 20 is the at minimum the product we would get. If we have 22s, we would reach a product of 2 to the power 20, which is about 1e6. If you reach a product of something like 1e6, in order to compensate that with the sum would be in the order of the values of the array only. So if you look at the constraints of the problem, n is 2e5. So if you are requiring the number of ones required, if they reach 1e6, then you know if the number of ones required, if this d becomes greater than n, then you can say that you can never have that many number of ones, because size of the array is your limit on the number of ones you can have. So this d would cross n very quickly. Even with just 20 number of integers, 20 number of greater than 1 values, we would cross 1e6 range. So we can say that the number of different R's that I would iterate through would be at max 20 only. After iterating to 20 greater than 1 values, for sure the difference would exceed the range of n. And if the difference exceeds the range of n, we can just break out that there is no use of iterating further. It would never come back to be equal to the sum. So for a fixed R, we are only iterating through at max 20. For a fixed L, we are iterating through at max 20 Rs. So basically we can say that overall we have reduced our time complexity to this 20 was something like log of AI or log of n only. N was the size array. So we have reduced our time complexity to n log n by iterating through just greater than 1 values. Is this logic kind of clear to you? If it is clear, we can move to the code. So what I'm doing here is, okay, through the code only, and I'll explain exactly how my algorithm is working. If it is not yet clear to you, then so we take the input. This input is done. Then in the vector v, I'll store the indices of all those. I'll store all those indices where my AI is greater than 1. I have to only iterate through those indices where my AI is greater than 1. So whenever AI is greater than 1, in V I push back I. So in I get the list of indices where AI is greater than 1. Okay. Now L I'll iterate through all the fixed L. Okay. L I will fix from 0 to n. All possible values of L. Okay. Now for any given L, when R is equal to L, then we have only one element in the array. So that would add a +1 to the answer. So that for that I do a answer plus plus. For R equal to L, I'll add a +1 to the answer. Okay. Now I have to move my R forward. So I initialize my sum with AL, product with AL. So whatever value we have at the Lth index, that is the current value of sum and product. Okay. Now I store L as the last index. So whenever I'm iterating to the next greater than one value. So if I'm here, I'm iterating through the next greater than one value. I'll store the last value, last index where I had iterated, so that when I iterate to the next value, I can add the number of ones present in the middle to my sum. Okay. So for that, I'm storing the last index. Now, from where I would start iterating, if I fix my L, the first value just after L, which is greater than 1. So in my vector V, I had the indices of all the values which were greater than 1. So whatever, so I can use a upper bound on this list of indices vector to get the R just greater than L. So upper bound on V just greater than L will give me the first R, which is just greater than L, and A of R is greater than 1. Okay. So the first value of non-1 R just greater than L, I calculate through upper bound. Okay. Now, while it is not equal to V dot n, so now I'll iterate through all the values in my vector V starting from this first, from the upper bound, whatever R I calculated, I'll iterate through all the next R's which are greater than 1. So while it is not equal to V dot end, I do it plus plus. In this way, I'll iterate through all the values in the vector, all the indices in the vector, starting from this. Okay. Now I'll do j equal to star it. So in j, I get the next index. So what would be my product in between whatever ones? Okay. So if my L was here, I iterate through the next R. If why is it not working? Okay, so if I'm iterating through the next R, then in between whatever one I get, that would not affect my product, but my product would be only affected by this particular value which is greater than 1. So product multiplied by AJ. Okay, and what would get added to my sum? This value of AJ would get added to my sum. Along with that, how many number of ones I have in the middle. So the number of ones I have in the middle would be current index j minus last index minus 1. So so if my current index is j, last index was I, number of ones in between is j minus I is this much, minus 1 is this much. Okay, so I add that many ones to the sum. So now my current product and sum are updated from L to current R. If this sum is less than P, okay, now if this sum is equal to P, I do NC plus plus. If this sum is less than P, I'll try to increase my R to make the sum equal to P. So how can I increase my R? I'll find that till where I have ones. Till what is the next index till where I have ones. So next is either N if the next of IT is equal to V dot end. If the current IT is the last non-one element, then N I would say is the index just after the last index. So that I can say is the next non-one element, or everything before N is 1, or the next of IT. If it is not equal to 1, then next would be star of next of IT. So next I would say is the next index where I have a element greater than 1. So if P minus S, this difference, plus J is less than next. So P minus S is the difference plus J. So if I'm at the current index J, currently I am at the index J. If I do add the plus D to that, then I'll reach the index where I want that. Till here I have to have all the ones. So if this is less than next, that means I can have all the ones till here. So I can do NC plus plus. Otherwise, I cannot do NC plus plus. And if this difference exceeds N, then I will just break out that I'm done. Now my difference has increased so much that even adding N times 1 would not make the difference come to 0. So then I would just break out. So using this break, I'll make sure that this loop is not running more than 20 times. Okay, so because of this break, it would make sure this loop is not running more than 20 times. So after this, I'll just print my answer. Okay, I hope the code is also clear to you. If you analyze the time complexity, this loop is running n times, and I explained why. Because of this break, this is running at max log n times. So this overall is n log n. So overall, I can say my time complexity is order of n into log n, and my space complexity would be order of n, which would be used for the vector v and array a. Okay, so I hope this problem is clear to you. Any doubts in this problem, or shall we move to the next problem? Okay, so the last problem from today is the last problem of div 1, which was not present in div 2. So if anybody had participated in div 1 and want to solve this problem, so I'm also bringing the solution for that, but I'll explain this a bit in short so that I don't bore you. I'm expecting whoever is coming till here had read the problem and has a bit of intuition about it. So this problem was stating that you are given a tree, and this subtree, I hope you know what it is. You have to assign a permutation for all the nodes of the tree, so that for any node which is not a leaf node, the value of the permutation is MEX of all the nodes in its subtree, all the values of the nodes in its subtree. So you have to make sure that this happens, that for any node which is not the leaf node, its MEX is, its value is the MEX of all the nodes present in its subtree except that node. If that value is satisfied for every non-leaf nodes, then that permutation is valid. You have to count the number of different permutations modulo this. Okay, so if this problem is clear, n was given as 500, but actually for even for some greater n like 1e5 also the problem can be solved. Okay, I'll show you how. Okay, I don't know where, I think the expected solution was something like n cube, but I have solved it in order of n only. So okay, let's look at the solution for this. I hope you know about the problem. So basically you are given some tree. Okay, and in this tree you have to assign some permutation. Let's say for this 1 2 3 4 5 6 7 8 9, n was 9. So you have to assign some permutation from 0 till 8. Okay, assign some permutation from 0 to n minus 1, so that for any node, let's say you are looking at this node, then for this node, if you consider all the nodes in its subtree except this node, then whatever is the MEX of the values at those nodes, that should be equal to the value of this node. That is the thing you have to make sure. So now let's come to the solution. So if you just think of some random tree, when would it be possible? So whenever you have something like MEX, what is the MEX of some sequence? It is like MEX of some sequence is like minimum value which is not present. So if 0 is not present in the sequence, MEX is directly 0. If 0 is present, then you would check whether 1 is present. 1 is not present, MEX would become 1. 2 is not present, it would become 2. Likewise. So if you just look at the 0, so if you start with the root node, okay, let's say this root node had some subtrees, okay, and then this subtree had some leaf nodes. Let's say you assign some value to the MEX. Let's say MEX of this, let's say n was 10 here. Okay, let's say for this root node you assign 5. So if you assign 5 in this root node, what you need to make sure? You need to make sure that all values from 0 to 4 are appearing in this subtree. Okay, okay, so now let's move to one of its subtree. Let's say to one of its subtree you assign some value 3. If you are assigning some value 3, that means in its subtree 0 to 2, all the values from 0 to 2 should come in this subtree. Okay, so in this subtree 0 to 2 should come. Let's say for this node you assign some value 6. That means in this subtree all values from 0 to 5 should come. Let's say here you assign some value 8. Here 0 to 7 everything should come. Now, is it possible that 0 to 2 comes in this subtree also, this subtree also, this subtree also. This is not possible. You can like look at it. So if you just think of 0, we can just say that this type of tree would be invalid, provided that all of them have some leaves here. If any of this node is a leaf, then you can assign it anything. There would be no condition for that. But I'm telling that for this node, all these three nodes are not a leaf. So if they are not a leaf, then 0 can be present in either this subtree, or that subtree. Then any only any one of them, in any one of the subtree you can have 0. For rest of two of the subtrees, both of these values would become 0. That means you are having 0 three times. This is not possible. So you can say whenever you have a tree, okay, now let's say instead of 3 subtrees you had only 2. Was it possible? Now, so from root node you had 2 nodes coming out from the root node, and for both of these nodes there were some nodes coming out from that. They are not the leaf nodes. I'm telling this is not the leaf node, and this is also not the leaf node. Then if you look at 0, if you have 0 somewhere in this, then you would say this node would become 0. If you have a 0 anywhere here, if you assign a 0 anywhere here, this node would become 0. So you have 2 times 0. And if you have a 0 anywhere here, this node would become 0. So you have 2 times 0. So that means this case is also invalid. Here also you cannot have any valid assignment. So the answer would be 0, no valid assignment exists. So how can you generalize this? That when would you have 0 valid assignments? So whenever you find that in the tree you have a node, for that you have 2 children, this tree has 2 children, such that both of these children are not leaf, then you can say by generalizing the above thing that your answer would become 0. There are no valid assignment. So whenever there exists a node having, whenever you have a node having greater than equal to 2 non-leaf children, so if any node has greater than 2 non-leaf children, we can say that no valid assignment exists. Our answer is 0. So this you can easily check. Go to every node, check all of its children, how many of them are leaves. Checking for a leaf is, if a node have no children, it is a leaf. So once you have created the adjacency list for the tree, you can easily check this in order of n. And once you check this, for all those structures of tree where this thing is valid, that there exists a node having greater than 2 non-leaf children, answer would become 0. Okay, so now the problem only reduces to all those type of trees where you only have nodes which have at max 1 children, which has at max 1 children which is not a leaf. So what would be the kind of structure of that tree if you think? So let's say this is the root node, it has 1 children which is not a leaf, rest all the children are leaf. Then again it has 1 children which is not a leaf, rest you can have some of the leaves in this. Then again maybe it doesn't have some leaf, this node has some leaves. Okay, and it ends here. So if you look at these non-leaf nodes, all the non-leaf nodes would be in a single straight line. If you just consider the non-leaf nodes in the tree, they would be in a single straight line. And for every node which is not a leaf, there would be some number of nodes which are leaf. So we can draw this tree like this, that starting from first node, this is a straight line of nodes which are not leaf, and in that you would have some, okay, let's have them one side only. In that you would have some, every node would have some x number of leaves attached to it. Okay, it may have 0 leaves, it may have some number of leaves. This last node would also have some number of leaves. So this would be the structure of the tree for which you have to find the answer. Now, what would be, how can you compute your answer for this type of tree? So just think, let's start from the bottommost node. So if you look at this node, for these three leaf nodes, for leaf nodes, you can assign any value from the range 0 to n minus 1. So there are total n available options. Let's say this node had 3 leaves. So for these 3 leaves, just assign any 3 values out of these n nodes. Okay, then for this node, what would be the value that should be assigned to this node? Would be the MEX of these 3 leaves. So if let's say in these 3 leaves you assign 0, 2 and 5. So their MEX would be 0 is present, 1 is not present, 1. So if from 0, 1, 2, 3, 4, 5, 6, 7 up till n, basically whatever you assign to these leaves nodes, just remove them. From the remaining value, the lowest value would be your MEX that would be assigned to this node. So this also got removed from the available. Now for this particular node, for the leaves of this particular node, again these leaves can take any value. So among the remaining value, there are 2 leaves. Just assign any 2 of the values to the 2 leaves. Okay. Now, if there was some different assignment to these leaves, would the number of ways of assigning to these leaves change? What were the number of ways to assign to these leaves? Out of n nodes, we have to choose 3 nodes. So here n c3 was the number of ways to assign, or np3 we can say that nc3 into factorial 3, that we can rearrange the numbers in the leaves to have different permutations. Okay, so we can say number of permutations, choose 3 are the number of ways to assign for these leaves. Once we have assigned any 3 values, we can consider the remaining values as a new permutation for which we have to do assignment to the rest of the tree. So picking any 3 values doesn't affect the remaining tree, that we can say. So these are the number of ways to pick values for this. And after 3 values are chosen, the minimum value would be automatically assigned to this. Here you don't have a choice. For this node, you don't have a choice. Whichever was the minimum remaining would be assigned. After this, 4 values are cut out. Remaining values are n minus 4. So for these 2 leaves, what would be the number of ways to assign to these 2 leaves? Out of the remaining n minus 4 available options, choose 4 options and choose 2 options. Choose 2 options for the 2 leaves and permute them. So the number of permutations, choose 2, would be the number of ways to assign to these leaves. And after assigning these 2 values, among the remaining n minus 6 values, whichever is the lowest would be the MEX of this. So let's say for this you assign values among the remaining, let's say you assign 4 and 7. So here you assign 4 and 7. So 4 and 7 were cut out. Minimum remaining value was 3. So 3 got assigned here. 3 got cut out. So after this, out of the n minus 4 values, you choose 2 values for this. 1 value got automatically assigned to this. Now the remaining values are n minus 4, minus 3 and minus 7. So out of the remaining n minus 7, whatever are the number of leaves here, they would choose from the remaining value. So from the bottom, we can move ahead. And this way, this is the number of ways to assign to these leaves. This is the number of ways to assign to these leaves. That way we can move till the top node, whatever would be the number of nodes remaining, among them number of leaves remaining. From that you can apply this NPR formula and get the number of ways. All these ways multiplied together is your final number of ways. I hope this thing is clear to you. So this overall thing can be calculated. So like a DP, you can calculate that whenever you are at this node, then for this remaining subtree, what are the number of ways? So for this node, number of ways for this node multiplied by number of ways here. So you can say that your DPI is whatever is DP of, let's say the only, J is the only child of I a non-leaf child of I. Let's say j is the only non-leaf child of I, then we can say dpi is whatever was the number of way till gpj. Okay, we would iterate only through non-leaf nodes. We will compute dp for only non-leaf nodes. Okay, leaf nodes, we'll just keep a count for every corresponding non-leaf node. Okay, so dpi we can say is dpj multiplied by number of, what would we multiply with? Number of nodes remaining, number of choices remaining, c number of leaf nodes. So what is the number of choices remaining? Number of choices remaining would be, so in this subtree how many, so here it was -4. Why was it -4? Because number of nodes in this subtree was 4, so 4 values were removed from n. So remaining is n minus the subtree size of j. So whatever is the n minus subtree size of j, that we can say is the number of nodes remaining. So this multiplied by n minus subtree size of j, c, what would be here? The number of leaf nodes. So the number of leaf nodes would be, you can say, whatever is the adjacency I dot size is the number of childs of I minus 1, because one child is a non-leaf node. So this way, whatever is the number of leaf nodes, that factorial number of leaf nodes. If you multiply by this particular thing with dpj, this way we can write out the transition for our dp. Okay, and if you can pre-compute these ncr, so ncr is just factorial this by factorial this, so this we can write as npr. Okay, npr is factorial n by factorial n minus r. That's what we are computing here. This whole thing can be written as n minus size j p leaf. Okay, this we can replace instead of that, where npr is this. So if you have computed factorials for n can range up till 500, so just pre-compute all the factorials modulo m up till n and inverse factorials, then this npr can be computed in order of 1. So if you're computing this in order of 1, the transition overall is done in order of 1, and you have in total n states at max. So in overall order of n time complexity, we have solved the problem. So I don't know what's the problem. So in order of n time complexity, we have solved the problem. Okay, so let's look at the code for this. Okay, so let's look at the code. So what we first do is, in our main function, I'm just computing all the factorials till 1e3. So fact pre-compute function, these I already have in my template, so I don't require to write it again, but okay. I pre-compute the factorials till n, and I also pre-compute the inverse factorials till n, so that if I don't compute the inverse factorials, you can do it in log n time by calculating mod inverse. But okay, this mod inverse functions I have written in binary exponentiation to compute the inverse. So this way I pre-compute the factorials and inverse factorials up till 10 to the power 3, which would be used. Okay, now in my actual function, what I'm doing is I take the input. So the number of elements in the tree, the number of nodes in the tree, and I've taken as a global variable because it would be used in my DFS. And I've used the adjacency list and DP and size. These variables would be required in my DFS, so these I've declared as global. Then I do adjacency dot assign, and I take the input, update my adjacency list. So this input part is done. Once input part is done, I do dp dot assign it to -1, size dot assign. In size, I'm computing the subtree size, because this subtree size was required for calculating my dp, as well as checking for this first condition, whether any node has greater than 2 non-leaf children. So you can say when the size of a subtree size of a node I is equal to 1, that is a leaf node. That is also another way to say that. Okay, so I'll pre-compute the subtree size and DP. I run DFS starting from the root node 1. Okay. Now I'll check if I'll compute the size of the subtree. So size of the subtree is 1, and when I'm iterating through all the values in the adjacency list of X, I do DFS So in this way, I do the DFS, and after running through the DFS of I can update my size of X plus equal to size of I. This way, I'll update the subtree size of X. Okay, so this way I calculate the subtree size of X. Now, if adjacency X is empty, that means this is a leaf node. So I don't need to compute my DP for the leaf nodes, as I explained. I'm only computing my DP. This DP is being computed only for the non-leaf nodes. Okay, so I do a return. Now I start with count equal to 0, and in count I would count the number of non-leaf children of I. Number of non-leaf children of I. If that number of non-leaf children is greater than 2, I can say that my DP is 0. My final answer would be 0. So if for any of the child the size of I is greater than 1, that means it is not a leaf. If it is not a leaf, I do count plus plus. Okay, and I also do dpx equal to dpi. So as I told, dpi is equal to dpj. So for dpx, I is basically its non-leaf child. So dpi, or we can say dpx, is assigned dpi. Here my I was the current node and j was the child node. Here x is the current node and I is the child node. So this I'll initialize to my dp. Okay, and if count is greater than 1, then obviously the number of non-leaf nodes are greater than 1. I do dpx 0. Otherwise, if count is 0, that number of non-leaf nodes is 0, that means it is the bottommost node. So for that, I will write the base case of my dp. The base case of my dp would be just multiply by this particular NCR. Okay, so it's NPR n adjacency x dot size. So for this, number of available nodes are n, and number of leaf nodes are size of the adjacency list of this node. So NP, size of adjacency list. This way I assign the base case of my DP. And in the else part, when count is greater than 0, when count is equal to 1, exactly equal to 1, then I've already assigned dpi equal to dpj here. So in dpx, I'll just multiply npr of n minus size j and leaf. So what is n minus size j? So size j can be written as whatever is size of the current subtree minus the number of leaf nodes minus this current node. So we can say that size is n minus size. So it is n minus size minus adjacency x dot size. So the number of leaf nodes is adjacency x minus 1 plus 1 here. So adjacency x is the number of nodes that we are subtracting from this subtree size. Okay, so the number of nodes adjacent to it is the number of nodes we are subtracting to get the subtree size of the remaining node. So n minus size of x plus adjacency dot size. In this way we get, this is same as n minus size of the child of that. Okay, and this other thing is number of leaf nodes is adjacency I is minus 1, size of adjacency x minus 1. Okay, so this multiplied by npr, and npr I'm computing as factorial of n into inverse factorial n minus r. Okay, this is what npr is, n factorial by n minus r factorial. So this I would return in my dp. So this way my dp is computed after the dfs. So my final answer is dp1. dp of the root node would store the total number of ways for this whole tree. So this way we can say that this whole DFS is taking order of n time only. Okay, these DP transitions are order of 1 because NPR is running in order of 1 only if we have pre-computed. So this is taking order of n time. These all input part was taking order of n time, and this pre-computation is taking some order of 1e3 time. So we can say that overall our time complexity is order of n only plus some pre-computation for the pre-computation till n, whatever n was there, pre-computation till n. So it's n plus n only. So we can say order of n is our time complexity.
and space complexity would be order of n for the adjacency list, and for the dp and for the size vector all are of order of n. So this is our time and space complexity. So even for something like 1e5 it would get accepted. Okay, I think the expected solution was something else, that's why constraints were given as 500, but this was an even better solution. Okay, so I hope this is clear to you, and thank you so much guys for tuning in. Goodbye.